Yeah, so number 10 I got on my own, I'm pretty sure. And then number 8 I circled because I'm really unsure on the domain and range sort of thing. So could we start with that one?
Yeah.
All right.
The domain you have is perfect.
Okay.
The range you have is perfect.
Really?
Uh-huh.
All right.
In other words, here's the thing.
Mm-hmm.
That dictates the domain. If x is not greater than or equal to -4, then we're going to be taking the square root of a negative number. You cannot do that. So that's definitely the domain. As long as x is greater than or equal to -4, then you will not be taking the square root of a negative number.
All right.
Now, furthermore, that part is always positive. The square root of any number is always positive. It's never negative. If it's always positive, then the range, the lowest point the range can ever be is -1. And it can be greater than -1, but even if this was 0, the range would be -1, and it can never be less than 0.
Mm-hmm. Okay.
I don't know how many questions are here, but typically at this time of year, somebody gives me a whole semester's worth of review that they want to do in an hour. So I want you to tell me which problems you want to do.
All right. I've already done quite a bit of the packet. I'm just, well, on separate pages and everything like that, and we've gone over a lot in class. I just kind of wanted to skim over some of the topics I was less sure about.
You direct. So, tell me which number you want to review.
Can we go over number 11?
Okay. We can back up if you need to. In other words, if you're not sure. All right. These are exponential equations. They're not algebraic equations.
Mm-hmm.
The difference is the variable is in the exponent. It's not on the algebra line.
Okay.
Now, most of the time, when you're solving exponential equations, you need to use logarithms. But occasionally, they will give you a problem where there's a common exponential base between those two numbers. What is it?
Between those two, is it 6?
Huh? So the left side, I can write this way, and always put it in parentheses, because the parentheses are necessary. And the right side, I can write that way. Whoops, minus v, not -4.
All right.
Now what?
Now, you just have to basically solve for the exponents instead.
Well, what do you do when you have double exponentiation? Use your rules of exponentiation. What does the left side become?
Would that be 6 to the 6v plus 4?
Uh-huh. In other words, we're going to multiply the exponents. The right side becomes this. Now we got the same base. because we have the same base, we can equate the exponents. That has to be equal to that. So I can say 6v plus 4 equal, excuse me, minus 3v, and then move the minus 3v to the left. You got minus or plus 9v, move the 4 to the right. Got minus 4v equals minus 4/9.
All right.
Now, remember this is an exponential equation. And I'm saying 99% of exponential equations, you need logarithms to solve.
All right.
But when they first start teaching you about them, they give you a lot of problems that have common exponential bases. In other words, 6 is a common exponential base for 36, and it's also a common exponential base for 216. So the fact that I was able to write these numbers as 6 to some power allowed me to solve it without using logarithms.
All right.
Those are the only ones you're going to be able to do that on. Normally, you got to use logarithms to solve exponential equations.
Okay.
So, let's look at number 12. First step on 12.
Subtract the 9 to get the exponential number on its own.
Now, is there a common exponential base between these two numbers, 15 and 73?
No.
Okay. That means we cannot use the previous method. The only way to solve it is with logarithms.
All right.
And typically, when you have this kind of an equation, the best way to proceed is just to take the natural log of both sides. Remember that step. That's a key step. Now, what does that allow me to do with this 9v? Now that this equation is in logarithmic form.
Now you can solve for it much easier because
I can move it to the front. In other words, perhaps the most important rule about logs is that exponents of the argument can be moved onto the algebra line, giving me this. Okay, you see how I got from this to what's below it?
Yep.
Okay, now that's just a number, so is that. So what's v going to be equal to?
V is going to equal natural log of 73 minus natural log 15.
Well, hold on. Let's do it algebraically. At this point, we can do it algebraically. 9v is equal to the natural log of 73 divided by natural log of 15.
Divided by?
Yeah, in other words, that's just a number. So I'm dividing both sides by natural log of 15.
Yep. Okay, I see that.
Okay. And now v is equal to that divided by 9. So that's our answer. And if there's anything about that you don't understand, say something and I'll go over it again.
Yeah, I understand it. For a minute there, I just thought that it was 9v plus natural log of 15 instead of multiplied by. I just didn't look at the problem that closely.
The key to logarithms is that these are just numbers, okay? And think of them as numbers. Well, if that's just a number, then it's another number multiplying 9. And I've got to divide by 9 times that.
All right.
Hold on a second. Let's see. We just did 12, right?
Yep. And then the next is the graph. Yeah.
Yeah, hold on a second. I need to shrink it a little bit before I can take a picture of it. Okay. First of all, let's talk about y equals b to the x when b is greater than 1. That looks like that.
All right.
When y equals b to the x and b is between 0 and 1, which I'll say is less than 1, the graph looks like this.
All right.
Well, this is a number between 0 and 1, correct?
Mm-hmm.
So the graph is going to be something that looks like that.
Yeah.
All right. Now, it also has this multiplier of 4. What does that do?
That
Hold on 1 second. Before I ask that, let's go ahead and plot y equals 1/2 to the x before we deal with that multiplier. We know it's going to look like that, but there's something else very specific to these equations, and that is when x equals 0, y equals 1.
Okay.
So they all go through that point. So it not only has that shape, but it has that point, and it gets closer and closer and closer to the x-axis. In other words, when you take a number less than 1, and you start squaring it, cubing it, quartering it, it gets smaller and smaller and smaller. Never quite gets to 0, but it gets close.
Mm-hmm.
The fact is that any number to the 0th power is 1. So I could say 1/17 to the x power, and it's still going to go through that same point. When x is 0, that's 1.
Mm-hmm.
I could say 1/1,000,000,000. And if I take that to the 0th power, that's 1. So it does not matter what is in the parentheses. It is going to go through this point, 0, 1.
All right.
And that's a huge thing to realize about exponential functions. They always go through that point. And it doesn't really matter whether b is greater than or less than 1. If b is greater than 1, it still goes through that point, and it goes up like that. In other words, if I had y equal 2 to the x, that might be the green line. In other words, if this is greater than 1, it's going to be the shape of the green line. If it's between 0 and 1, it's going to be the shape of the black line.
All right.
So, what do we have here? We have the primary part is this part. That tells us the shape.
Mm-hmm.
That is my black line. So let's erase the green line. Now, the effect of the 4 what is the 4 really going to do?
It's going to expand the amplitude of it?
Well, yeah. In other words, whatever the y value would have been, it's going to make it 4 times that. So this point right there is going to be right here.
Okay.
This point right there is going to be way up here, 4 times further away from the x-axis.
All right.
This point right there is going to be 4 times further away from the x-axis. And the net effect of that is this kind of a shape. It still approaches the x-axis. So it still has a very similar shape. It's just this 4 is a vertical stretch factor. It's no different than a polynomial. When you are multiplying from outside the function, then it's a vertical stretch. Every point that was on the black curve, if I go find a point on the black curve, like right there, on the red curve is going to be 4 times further away from the x-axis.
All right.
That's how I get the red curve. And the red curve is everything. In other words, there's nothing else but that. There's no reflections, there's no horizontal shifts, there's no vertical shifts, any of that.
All right. Next page.
Okay.
Then on number 14, you're just finding the inverse of the function.
Yeah, let's do that. Inverses can be tricky, but in general they're fairly easy. There's only 2 steps. What's the first step?
Flip it.
Switch the variables, not flip it. Flip it would be this. That would be flipping it.
So switch the y and the x?
Yes. Switch the variables. Remember, that's always the first step. So we got x equals 1 over the 5th root of 5 to the y. In other words, all I've done is switch the variables.
Awesome.
The second step is to solve for y. And once you solve for y, you will have the inverse.
Okay.
So how do I solve for y?
So the first thing you'd have to do is get it, or square it, or like put it to the 5th power to get it away from the 5th
Hold
root.
on. Let's first of all get y in the numerator. And I'm going to do that by doing this. You understand how I got that step?
Yep.
Okay. Now I'm going to take each side to the 5th power. What do I get when I do that?
You get 5 to the y equals 1 over x to the 5th.
This is an amazingly difficult problem. I'm surprised they are giving it to you. But nonetheless, let's continue through it.
All right.
Now, do you know how to solve for y here?
In this case, you have to take the log of it.
Okay. Log base what?
Log base 5 of y. I'm not sure how to set that one up. I don't know.
Well, first of all, let's simplify this. It's 1 over x to the 5th. And now, there's a couple of ways to do this. We could take the log base 5 of both sides. And that's not a bad step, because what does that produce on the left side?
On the left side, that'll get you, or that can get you y on it too, yeah.
That's y, and that's what we're trying to solve for. So that's very valuable, being able to reduce the left side to that. And now we have that. So we have the log base 5. Let's call that x to the minus 5. First of all, do you see how I can write that as x to the minus 5?
Yep, because with that minus it flips the reciprocal.
Yeah, okay. And now I can move that minus 5 down in front. So I get this. And that's what y is, but it's not really fair to call it y. It is not the same y as that. It's the inverse of y. And that's what the inverse of y is. So when you learn that the two steps are switch the variables and solve for y, when you find an answer for y, you really have solved for y inverse, not y.
Okay.
Now, I don't think I can do much to that in terms of simplifying it. I could say, well, I could take it back one step and call it this, but not sure which one is more simplified. I gotta think that this one is the more simplified version. Minus 5 times log base 5 of x.
Okay.
Alright, these are really simple. You want to make sure you can do these because you're going to get lots of these on your final. In other words, there are some problems you're going to get lots of, and there are some problems you're only going to get one of. Let's focus on the ones you're going to get lots of, right?
Oh, yeah.
Alright, so when you have a problem like this, start with the numbers, then do the next variable, then do the next variable. So what do the numbers equal?
Right now, do they equal 0?
2 times 4.
8.
Now go to the a variable. What's a to the minus 3 times a to the plus 3?
A to the minus 3 times a to the plus 3. That would make it a to the 0, so 1.
Okay. We'll even write it as a to the 0. And now what's b?
B to the 4th times b to the 3rd, so b to the 7th.
And now we'll turn that a to the 0 into 1. So this is our final answer.
All right.
In other words, any number to the 0 power is 1, always. It can be 1700 to the 0th power, it can be x to the 0 power, it can be a to the 0 power. They're all equal to 1. One of the most important things you can remember in math is that any number to the 0th power is equal to 1.
All right.
Shrink this a little bit more. What's the parent function. In other words, you have approximately 10 elementary functions that you've been taught. Y equal mx plus b, y equal x squared, y equal x cubed, y equals sine of x, y equals square root of x. About 8 to 10 of them. And if there's one thing you want to remember in math, it's what each of those looks like, how they graph.
Okay.
What's the parent function here?
Of this one, it's going to end up being the same kind of graph as the last one. So is it the y equals 1 over x?
1/7 x.
1/7 x.
That's the parent function. Now, does that go lower left to upper right, or does it go upper left to lower right?
Upper left to lower right.
Okay. And this point right here is what?
1.
0, 1.
Yeah.
Put the x and the y coordinates on it.
All right.
Now, the fact that our function is 1/4 that, what's the effect of the 1/4? In other words, now we want to start looking at it as a transformation.
Okay.
What's the 1/4 do? If we're looking at it as a transformation, the 1/4 is a vertical what?
Shift.
Shrink. Is that what you said?
Yep.
Okay. Now, what that does is it shrinks this point down to there, which is now 0, 1/4. And it shrinks every other point on this black curve down by 1/4. So it gives you a curve kind of like that, which flattens out that curve. In other words, when this is kind of a difficult thing because it's not easy to see a exponentially declining or decaying curve flattened out or steepened. If I was going to steepen it, it would look like that. All three of those curves are asymptotic with the x-axis. But this one is steep. This one is normal based on the 1/7. And this one is flatter. And it's flatter because 1/4 is a shrinking. That is a vertical shrink. So that every point that was on the black curve is now 4 times closer to the x-axis. In other words, this point is 1/4 of that point.
All right.
And that's really the way to think about it, because then you don't really have to memorize whether it's a stretch or a shrink. You can just kind of draw a few curves and figure it out.
Okay.
That's the best kind of math, is when you don't have to memorize, you can figure it out.
Yeah. Sure.
It's this one.
Then write each expression in exponential form.
Yeah, how can I write that in exponential form? First of all, radical signs aren't very useful in higher mathematics. They just aren't, okay? So every time you see a radical sign, once you get beyond precalculus, start thinking about converting it to an exponent. What is square root of 6p equal to?
So the square root, that would turn into the exponent of 1/2, so 6p to the 3/2.
Well, then we're going to cube it. So this is really what that says. The first step is to convert the radical sign, because Radical signs suck in math, but exponents don't. Everything you do higher than what you're doing now will want an exponent, not a radical sign. So the first thing we convert is the square root of 6p means 6p to the 1/2. We still have it all being raised to the third power, and you correctly surmised that we multiply the exponents, so we get that. Now, write each expression in exponential form. That's a good answer.
Okay.
Now, it wouldn't always be a good answer. If I gave you this number, that would not be a good answer. Why?
16 can be, or has the square root of 4.
What should this read instead of 16 to the 3/2?
4 to the third.
64.
64?
Uh-huh. That's 4 to the third.
Oh, because...
You were right. You were right, but take it all the way down. In other words, turn it into a number if you can. Now, in the problem we're looking at, notice that the very first step would be to take the square root of 6, which is not a rational number, then to cube it, which is still not a rational number, and then do the same thing to p. Well, since we do not produce integers, we don't do any of those steps. And the final step is 6p in parentheses to the 3/2. That's going to be your answer. If that was 16p, that would not be the answer, because I could take the square root of 16, which would be 4, I could cube it, the answer would be 64p to the 3/2.
All right.
But since we have a number that exponent is not going to turn into a whole number, we don't do it. That's kind of the rule with math, is if you can reduce it to an integer, you do it. If you can't, you don't.
All right. Cool.
So 5x to the 3/2 equals 625. What's our first step here?
The first step is to take 625 down to match 5. Like put 625 in exponential form?
No.
No.
No, the only reason that's not our first step is there's no x on the right side. If there were an x over here, that'd be a good first step, because then I would have some number, I would have x, and I would be able to equate the exponents. But when you have an x, this is an algebraic equation, not an exponential equation. In other words, the variable is on the algebra line. Well, the thing we want to do is isolate that for starters.
Yep. Okay.
How do I isolate that?
Divide both sides by 5. So x to the 3/2 equals 125.
And how do I solve that?
You would have to cube or put each side squared and then to the third root.
Yeah, the easy way to think about this is to take the reciprocal, like that.
All right.
In other words, that's always going to turn this into x, right? Because we're always multiplying those. And if you want to turn it into x to the 1, you got to multiply it, or you have to, exponentiate it by the reciprocal. So x is equal to 125 to the 2/3. Now, how do you do that one?
Well, 5 cubed is 125.
Okay.
And then, see here, 120.
Always do the root first.
Always do the root.
Always do the root first. Always. What's the cube root of 125?
5.
Now what's 5 squared?
25.
That's the answer.
All right.
That's why you always do the cube root first. Because the kind of problems they give you are like this. What's that equal to?
8 to the 2/3. 4?
Yep. As long as you do the bottom first, it's always going to come out nice. And in case you're wondering, they're never going to give you a problem like this. Unless they say it's a calculator problem. And that's because the cube root of 7 is not a whole number. So they're not going to give you this. The only thing they give you are things where the cube root is an easy number. What's that equal to?
25.
Hold on, up here.
Wait, where are we? Oh, there it is. Okay. 27. So then that's 3, 9.
Huh? Okay. So always do the bottom first. Because if I were to, I could do them in either order. But if I do the top first, it's 27 squared. Then I got to take the cube root of that. Well, now I need a calculator. I don't know what 27 squared is, but I would do that, and then I would take it to the 1/3 power and come up with my answer. But my point is that if you do the numerator first, you're always dealing with gigantic numbers. If you do the denominator first, you're always dealing with small numbers.
Awesome.
You always want to deal with small numbers. Just like if you have a choice of dealing with negative numbers or positive numbers, always choose positive numbers.
Mm-hmm.
All right, 16x all the 1/4. Simplify that.
Well, 16 to the 1/4, that's 2, right?
Yep.
And then x to the 4th to the 1/4 is x. So 2x?
Perfect.
Awesome.
Go to the next page, I presume. I went left to right, correct?
Correct.
All right. Amazing how it improves the resolution as you go down. Let's see. How far did we go down here? I think this is the same page.
Is it?
I believe it is. Yeah, it is. 19 was the last problem we did.
Yeah.
Let me go to the next document here. All right, this is different. That's a z.
Yep.
So we have
log 5.
The log base 5 of z to the 5th root x. Boy, they don't start you on beginner problems, do they?
Oh, no.
So it says expand it.
Okay.
So let's expand it by steps.
All right.
Starting probably with the multiplication.
Okay.
But again, the radical sign doesn't do you any favors here. Let's change that radical sign. What are we really looking at?
Log base 5 of z to the 5th x to the 1/2.
Now we can deal with it. Because now we have rules that cover exponents. We don't have rules that cover radical signs. So, first of all, separate those two. into two log expressions.
Log base 5 of z to the 5th and log base 5 of z to the x. Or, sorry, x to the 1/2.
Plus. Very important. In other words, the log rule that we're using is the log of a times b equals the log of a plus the log of b. Super important. If I'm doing multiplication in the argument, I'm doing addition with two separate log expressions. So you see how I got from there to there?
Yes.
Okay. Now, I can expand it further because another rule of logs says that you can take that exponent and move it to the front right there. In other words, let's take it out of the exponent and put it as a coefficient. So now what do you get?
So then that'll be 5 log base 5z plus 1/2 log base 5 of x.
Yeah, and you can only use these rules if the base is the same.
All right.
In other words, if one was base 4 and the other was base 5, these rules don't apply. You can only expand and condense if you're dealing with the same base. But when they say expand, they mean expand fully. Get rid of all exponents and turn all multiplication or division into addition and subtraction.
All right. So
the next one, find the inverse. What are the two steps?
The first step, switch x and y.
Now we got to solve for y. What should we do?
First, you'd want to move the 10 to the other side first,
Yeah,
right?
in other words, I want to isolate that first. That's my goal, is to isolate that. So how do I isolate that?
Would you divide by 10?
So I got x divided by 10 equals log base 2 of y. Now here comes the tricky part. How do you solve for y at this point? It's not clear. Let me explain. If a equals b, then 3 to the a equals 3 to the b. And in fact, 7 to the a equals 7 to the b. You follow this logic?
Mm-hmm.
Well, whenever I have something is equal to the other, like I do in our equation, I can always make these exponents of some base. Well, the base I'm going to make them exponents of is 2. Why? Because that turns into y. Because that 2 is the same as that base, it's always equal to that. In other words, if I have base to the log base b of x, that's equal to x. Always.
Mm-hmm.
So when I get that situation, it's a nice situation because it's equal to whatever this argument is. And that's what I'm trying to solve for, is y. So I end up getting y equals 2 to the x over 10. And
Yep.
that is the inverse, so I'm going to call it y inverse, not y.
All right.
That's the answer. And this is kind of a, I don't know, you probably have never seen this before. But let's talk about it a little bit more because you're going to see it more in the future.
Okay.
Whenever you have the log of y equals something like x cubed plus 1, let's say we had that, we're trying to solve for y.
Mm-hmm.
What's the base of the log on the left?
The base of the log on the left is 10.
Okay, let's write it in there. So what do I want to use underneath if I'm going to let both of these be exponents on some base? What's that base going to be?
10?
Yeah. So I'm going to put a 10 there and a 10 there, parentheses there, and now I got 10 to the exponent of that equals 10 to the exponent of that. Well, that allows me to write on the left y. And the answer would be that. So whenever you're solving log equations where you have to solve for the argument, think of this method. Now, it's not the only method. In other words, there's actually maybe a simpler method here, and that is to put it in exponential format. What would it be in exponential format?
I have no idea.
Number on the far left
10.
raised to the power of the number on the far right
So x
equals the number in the middle.
equals y.
Notice that's exactly what I got when I did it the other way. Only this is really a lot easier. In other words, is all I have to do is put it into exponential format. And converting from logarithmic to exponential format, if you don't know how to do this automatically, we need to practice it. 8 equals x cubed. Put that in logarithmic format.
8 equals x cubed. So then, would that be log base 8?
No. Remember that logs are, this is always the base. So it'd be log base x of 8 equals 3. And if I wanted to put this back in exponential format, it's the number on the far left raised to the power on the far right equals the number in the middle. And I would know that x has to be 2. But being able to go between these two formats is the #1 rule for handling logs. You absolutely want to do that. Let me test you a little bit more. This will get half your problems right if you can do this. I'm serious. It's that important.
Okay.
Now, let me give you a few more here. Let me think for a second. X to the... No, let me do it this way. 2 to the x power equals 7. Give me the logarithmic expression of that.
So then that'll be log base 2 equals...
The base is always what's under the exponent.
Okay. So then log base 2 of 7 equals x.
The only thing you have to remember to be able to do this is one thing. Logs are exponents. So if I write a log equation, on the other side of that has to be the exponent. And then you just have to figure out where the other two numbers go. And this number is always the base, so it goes down there. There's only one place for the 7. It's there.
All right.
So at a minimum, you want to be able to convert these between logarithmic and exponential expression. Now I'm going to erase one of them, and I want you to tell me, put this back in exponential expression.
2 to the x equals 7.
Yeah, and boy, I don't know. There's probably lots of ways to memorize this, but the easiest one for me is it's the number on the far left raised to the power of the number on the far right equals the number in the middle. It's the way I do every one of them. The first moment I see this, that's my thought process.
All right.
That was number 28, right?
Yep.
When you are graphing a rational function like that, it is hyperbolic in nature. In other words, it's going to look something like a hyperbola.
Okay.
Doesn't matter. What I've drawn here is y equals 1 over x. But even if you have x in the numerator and x in the denominator, it's still hyperbolic in nature. And that's a very important thing to realize. Okay? So, when you have something that's hyperbolic in nature, there are frequently vertical and horizontal asymptotes, and that's the first thing you have to do. What's the vertical asymptote?
The vertical asymptote, is it 3?
Vertical asymptote is wherever the denominator is 0. Not the numerator, the denominator.
Okay.
Where's the denominator 0?
4.
So there's the vertical asymptote. In other words, the one rule of math that you can never violate is you cannot divide by 0. No matter what, you can never ever divide by 0. Which means x can never be 4, because if x were 4, I would be dividing by 0.
All right.
Where's the horizontal asymptote?
This one would be 3.
The horizontal asymptote, when the power of the numerator is the same as the power of the denominator, in other words, they're both 1, then the horizontal asymptote is the ratio of their coefficients, which is 1. So y equal 1. If I had this function over here, on the right, what's the horizontal asymptote?
Is it 1 again?
It's the ratio of their coefficients. In other words, the highest variable in the numerator is x squared. The highest variable in the denominator is x squared. Whenever that's the case, it doesn't matter. It could be x to the 12th over x to the 12th. The horizontal asymptote is the ratio of their coefficients.
So 4/3 for the one on the far right?
4/3.
All right.
I didn't understand if that's what you said or not, but that's what it would be. 4/3. In other
Okay.
words, if I had y equals 17x to the fourth minus whatever, it does not matter what follows that. As long as x to the fourth is the highest coefficient and the bottom has the same thing, I could still have a 2 million x to the third. Wouldn't matter. The only thing that matters is the highest degree. That is the horizontal asymptote, 17 divided by 3.
Okay.
Now, when you're dealing with hyperbolic functions like we are, drawing your grid is absolutely the first step. Okay? Now
All
we
right.
know that it's going to look like one of two things. It's either going to look like that, or it could potentially be in the second and fourth quadrants. It's one of those or the other. It's either the black curve or the green curve. And
All right.
it's a relatively easy way to figure it out. Plug in some value of x, a simple value, which allows you to calculate what the others should be.
So
What value of x should you plug in?
maybe 10?
About a small number. Always, whenever you have a choice of plugging in values for x, boy, choose 0 or 1 or 3 in this case. 0
3?
would be a great one.
0. Okay.
So when x is equal to 0, what is f of x equal to?
F of x, f of 0. So.
Huh? Yep. What's it equal to?
Negative 3 over negative 4.
Which is positive 3/4.
24.
So I know that when x is 0, y has to be positive 3/4. Well, this dotted line is at 1.
So
Which curve is the correct curve?
the black ones in the first
Yeah,
and
I didn't draw it very good because I should have drawn it where at 0, f was equal to 3/4. So it really kind of gets drawn like that. Okay? But the fact is that I was definitely able to distinguish between first and third quadrant or second and fourth. So I know for a fact that it's not the green. It's the second and fourth. And when they say graph it, if you had anything close to what I have, in other words, even if you had what I had originally, which wasn't quite accurate, I just drew it like that. If your teacher does not give you full credit for that, they should be ashamed of themselves. That is a proper 100% answer. You don't need to have every point correct. I don't need the y-intercepts to be correct. Because all I need to do is know that I'm in the first and the third quadrant of the grid that I have drawn.
All right.
Which is based on the vertical and the horizontal asymptotes.
Yep. Cool.
Morgan, I got more appointments, so I'm going to let you go.
Okay.
When is your final?
My final is this coming Monday.
So you still got some time. Okay. Well,
yeah.
You need another session? I got time before next Monday.
Awesome. Thank you so much.
All right. Bye-bye.